Pluto remained for decades a symbol of extreme isolation, a distant body that science considered incapable of any significant activity. Classified as a dwarf planet, seen as too small, too cold, and too old, it seemed condemned to be merely a frozen vestige of the solar system's formation. However, the approach of the New Horizons probe in 2015 shattered this static image and revealed a world where signs of change, movement, and energy still persist. What was once considered a cosmic corpse began to look the opposite. The revelation was not only unexpected, it was disturbing to traditional scientific models, because Pluto did not exhibit the aged, cratered surface that would be expected of such an ancient body. It showed surprisingly smooth areas, as if part of its history had been erased. In a place where the cold should have paralyzed everything billions of years ago, something continued to act silently beneath the surface, smoothing impacts, reshaping the terrain, and maintaining processes that should not exist. From that moment on, the dwarf planet ceased to be merely a distant object and became a profound enigma. Its structures, textures, and compositions revealed a complex, unexpected dynamic that was difficult to reconcile with what was understood about icy bodies. Each discovery seemed to open new questions, leading to a complete reinterpretation of the geology at the edge of the solar system. And curiously, it all began with the absence of scars. The absence of extensive craters in some regions of Pluto was the first clear clue that something was terribly amiss. Ancient bodies, especially those so far away, should retain their marks. Impacts don't stop, they just cease to be erased. But vast areas on Pluto, especially the region known as Sputnik Planitia, appeared young, with surfaces so smooth they defied the very notion of the passage of time. The conclusion was inevitable. Active processes are renewing the terrain. This plain is not merely an area of static ice, it is composed primarily of nitrogen ice, a material that at Plutonian temperatures should be rigid, but which behaves almost fluidly there. Clear evidence of convection, such as giant polygonal cells, indicates that this ice is moving, slowly and inexorably rearranging itself. The surface regenerates, replaces itself, erases old signs. It is as if Pluto possesses a self-renewal system that defies logic. This behavior raises profound questions about the energy source capable of sustaining such processes. After all, sunlight on Pluto is too weak to support any significant dynamics. Therefore, the visible activity cannot be attributed to external heat. This leads to the unsettling conclusion that there is a minimal yet persistent internal energy source operating in an environment where only thermal silence was expected, and this energy manifests itself in other, even more surprising ways. Among these manifestations are colossal structures identified as possible volcanoes. Unlike terrestrial volcanoes, they did not expel molten rock, but rather frozen mixtures of water, ammonia, and other compounds. These cryovolcanoes suggest the presence of underground reservoirs that remain in a partially fluid state, indicating that Pluto's internal temperature did not drop to the point of freezing everything completely. The volcanic activity reveals a dwarf planet that remains restless. These icy volcanoes are immense and exhibit morphologies that could hardly be explained by passive processes. Their structures suggest repeated extrusions, layers expelled in different episodes, as if Pluto's interior insisted on releasing material to the surface. This directly challenges the assumption that small bodies cool too quickly to maintain any geological activity after a few billion years. Pluto silently refuses to freeze completely. To explain this, researchers have proposed that the heat does not come from the outside, but from within. Pluto's rocky core contains radioactive elements capable of slowly releasing energy through decay. It is a minimal, almost imperceptible process, but sufficient to keep internal layers warm enough to allow the existence of fluids. This residual heat, trapped beneath a thick crust of ice, creates an isolated environment where subterranean processes persist even under extreme conditions. If this isolation is effective, it could maintain not only partial reservoirs, but an entire subsurface ocean. And this hypothesis has gone from speculation to a concrete possibility. Observations of Pluto's gravitational field and studies of surface tension suggest the existence of an extensive layer of liquid water mixed with salts and ammonia, located beneath the icy crust. This ocean could be hundreds of kilometers deep. The existence of such an ocean completely alters the interpretation of Pluto. It ceases to be a frozen block and becomes part of the group of ocean worlds in the solar system, like Europa and Enceladus. This type of environment is considered one of the most promising candidates for the presence of conditions favorable to life. Not necessarily complex life, but chemical processes reminiscent of those that preceded life on Earth. And this, coming from a remote dwarf planet, is profound. Beyond its internal dynamics, Pluto also surprises with the composition and behavior of its solid surface. The mountains bordering the nitrogen plain are not made of rock, but of water ice so cold and rigid that it behaves structurally like terrestrial rock. This ice forms immense mountain ranges, supporting peaks and reliefs that contrast with the dynamic plain below. The coexistence of these materials creates a unique geological environment. These denser mountains float on lighter nitrogen ice, behaving like immense icebergs anchored in a slowly moving frozen sea. It is an interaction between solids that has no parallel on our planet. The dynamics are silent yet active, slow but constant. It reveals a natural engineering that operates on the boundary between freezing and movement, challenging conventional conceptions of planetary geology. Pluto also has an atmosphere, a fact that further challenges its classification as a dead world. Its atmosphere is thin, composed mainly of nitrogen, with traces of methane and carbon monoxide. But what is most impressive is that it is blue. This color is a result of the interaction of sunlight with particles known as tholins, complex compounds that arise from the reaction of gases in the upper atmosphere. These aerosols scatter blue light, creating an effect strikingly similar to the Earth's sky. This atmosphere, however, is not permanent. During its long orbital period, as Pluto moves further away from the Sun, it begins to freeze and fall onto the surface as a thin layer. When it approaches again, part of it sublimates and rises again. It is a climatic cycle spanning centuries, marked by extreme alternation between gaseous and solid states. A planet that freezes its own atmosphere is an unusual phenomenon and deeply symbolic of its liminal nature. Pluto, therefore, reveals itself not as a dead body, but as a survivor. A world that resists thermal paralysis and maintains internal activity despite the odds. It challenges the logic that once guided the definition of a habitable zone, indicating that worlds capable of harboring liquid water do not depend exclusively on solar heat. A rocky core with radioactive material and efficient insulation are sufficient. This perception dramatically expands the potential map of cosmic habitats by demonstrating that distant and seemingly inert regions can sustain complex processes. Pluto forces science to reconsider its search for life. It is a reminder that extreme environments do not mean impossibility, but rather a diversity of paths. Cold worlds can hide warm oceans, dark regions can sustain chemical reactions, and small bodies can have internal engines that endure against all odds. This dwarf planet has become a symbol of cosmic resilience, a silent machine that persists on the brink of absolute freezing, driven by internal forces that operate slowly but steadily enough to shape mountains, fuel volcanoes, and sustain oceans. Its complexity suggests that the universe does not only favor large illuminated worlds, but distributes possibilities even in the darkest reaches. The discovery that Pluto may be geologically alive has broken paradigms. It has opened doors to new investigations and broadened our understanding of how distant worlds function. It has shown that active geology does not depend on large mass or proximity to the Sun, but on specific combinations of structure, composition, and time. And perhaps it has shown that the frontier of life is much wider than we imagined. Ultimately, Pluto is a reminder that the solar system still holds profound secrets, hidden where we least expect them. By revealing itself to be active, it demonstrates that science is far from fully mapping the possibilities that exist beyond Earth. Each new detail adds layers to human understanding and invites us to explore not only what is visible, but what remains buried beneath ice, silence, and distance. Therefore, studying Pluto means studying the limits of the possible understanding. How worlds can maintain warmth, movement, and transformation even when everything conspires towards stagnation. It is a testament to the cosmos's capacity to create systems that defy intuition and challenge what we consider normal or habitable. And as long as mysteries persist on its surface and within it, it will remain one of the most intriguing pieces of the vast celestial puzzle. If this journey through the hidden nature of Pluto has sparked your curiosity, there is much more to explore in other worlds that also hold profound secrets. Keep following along and participate by leaving your comment, liking, and subscribing to our channel so you don't miss the next investigations. Each new video delves even deeper into this universe of discoveries, where the unknown is always the next step.